Okay, yeah, so this is encoding object similarities in SDRs, and that's the work I did for my internship. So a quick outline. I'll be going through some motivations, goals, and limitations in the beginning, and then we'll go through some play examples for how I compute similarity from evidences and how I encode those similarities into SDRs. And then towards the end, we'll go through some synthetic and Monty results. Okay, so in Monty we have sensor modules, and these modules they make some observations of let's say an Amenta coffee cup, and regardless of whether these are distance or surface sensors, they still get some features, and these features are later converted into some so in observation space, these features could be some patches or some RGB images or whatever. And then we convert those into features like hue or point normals or curvatures, and that's the job of the sensor module. And it does that so that the learning module that comes on top of it can take those features and can apply some similarity metrics to them. This is very important for generalization. So without it, the recognition will be very brittle, and we would not be able to, this is how we apply some tolerances on the features. And that's very important, because if we want to create this modular structure of LMs stacked on top of each other, then the higher level LM needs to take those, whatever is being sent from the lower level LM, and also apply some similarity measure on it so that it can do, it can be generalized to different object variations or feature variations. So this allows us to do something like this, and then Monty can then generalize to those features and figure out, okay, so we're looking at the cup, regardless of whether this cup is, there could be different lighting variations, or there could be different features in morphology or point normals. We can apply some tolerances and thresholds, and then we can still recognize that this is a cup. Now, the problem is in compositionality is when we add another layer stacked on top of it. What do we want to send to this higher level? This higher level is only looking at objects in a scene, right? So it knows, or maybe like, so at an set like this, we have like some plates and knives and utensils and stuff like that. And it knows the relations between them. And it knows that, okay, I'm looking at an object, but what is an object in a higher level scene? So what does it expect to see? So we have different options here of what we can send up. We could send up the full graph, and then the higher level is going to have to figure out how to apply some similarity metrics between the graph that it has learned and the graph that we're sending up, so that we can apply those tolerances. Otherwise, it wouldn't be able to generalize to different objects.
When you say send up the full graph, you mean all the location feature pairs?
Yeah, so like the mesh.
No one, there's never been a thought or consideration that we'd actually do that.
Yeah.
That's so gets rid of the whole point of having these learning modules, right?
Right.
Okay, so
we're not doing that.
Okay, so that's why she mentioned it.
Yeah.
No, we're saying what are our options? So one option could be that, but that's
well, I
not.
don't think that's an option.
Yeah,
but,
that's not.
that would be
it's a very bad option.
That would be a naive approach.
Right. That's the obvious.
But yeah, to your point, it would enable some degree of generalization, because you could compare graphs. It just wouldn't be it would be a terribly inefficient and weird way to do it.
The whole point here is you need to form representations that are constant over these variable inputs, and that wouldn't be doing that. That would be passing all the possible things. Okay.
But if somehow the higher level is able to compare these graphs, then it functionally would still work, but it's not really summarizing any of those objects into a single representation. What we really need to send up, and of course we can't send up just the object ID, because that assumes that all of these objects are equally similar or equally distant from each other. So we can't really apply any similarity metrics on those object IDs. If we send 1, 2, 3, we don't really know how 1 and 2 are related together with respect to the rest. So,
I'm going to push back on that a little bit.
Okay.
I mean, you're throwing a whole bunch of things in here in ways that I don't think about this. So you say you can't pass an object ID. It's not clear why you can't pass an object ID to me. I mean, you said because I lost similarity. I think the whole point of here isn't this whole exercise to ask if object IDs can be represented in a way that there is similarity. Isn't that the point of this exercise?
Yeah, I think he's saying when he says object ID is like an integer, like, oh, it's object 23 versus 42.
Oh, well, right.
I think that's what you
mean. In our theory, object IDs are always SDRs. It's never like that. So I refer to the object ID as an SDR. So I never refer to it as an integer. So if you're going to slip into putting in integers, then.
So
I know in some versions of Monty it was integers.
Well, maybe. I guess I'm thinking about.
That is how it currently is.
Okay.
So.
All right,
yeah.
great. I'm thinking about brain theory. So,
So that's the baseline that we're trying to improve on.
I mean, it'd be helpful to be explicit, like, oh, if we use another ID that was an integer, then it wouldn't be helpful at all.
Right. So now
I couldn't determine similarity.
Yes. So yeah, for object IDs, there is no similarity embedded in those IDs as integers, because we're just being able to separate them, but we don't really know if object ID 1 is closer to 2 and so on. So what we really want to do is send up some representation that encodes similarity such that these two cups are closer together than they are to the cereal box. So for example, if we replace those cups together, if we switch them and it senses cup 2 versus cup 1, the scene has some encoded tolerances so that it really doesn't matter. I mean, it's close enough to what it has learned. So it maybe wouldn't change the scene that it thinks it is. But if we, for example, change it to a cereal box or something like that, then it would need to say this.
So I don't know if I should just let you do your presentation, or should keep reading.
No, keep asking.
I mean, you made a statement. We can't, these things have to encode similarity. It's not clear to me that's the case. I mean, for example, we've talked about various ways of doing this. A model can consist of sort of morphology of an object, and that's independent of what the specific features of that morphology are. We've also talked about the orientation, which is sort of the morphology. Just the orientation of features is enough to recognize and see similarity between objects. So instead of, you might not think this is a monolithic thing you're passing up, but a model, what you're recognizing could be both morphology and specific. There could be two different things you're passing up. It's not that there has to be a representation that encodes both of those things.
Yes.
So that's an assumption that I'm not sure I would sign up to. Maybe what you did during your internship, but I'm just pointing out that's not something I would sign up to.
Yeah. When we get to the part where the limitations are, I'm going to explicitly say that this inherits the limitations of evidence LM, and when we do evidence matching, whatever we accumulate as extra evidence, that's going to go into the similarity, and that being some type. So when Vivian did this, she said, okay, so we have features, we can use those features to add evidence, or we could just only do for morphology or whatever is being used to add evidence. This is what we really use to create the similarity scores. So it really inherits the strengths and weaknesses of these evidences. So we're only sending one representation, one SDR representations, but and that includes whatever is being encoded in the evidences. If that makes sense.
I think the other thing is even if Jeff, we had something to merge these two representations into a generic mug morphology, which we probably do want to add as well. I think it's still useful to capture that mug is more similar to coffee cup, like a traditional coffee cup, or a soup can or whatever, than it is morphologically similar to something totally different.
Right.
So I feel like pooling together the kind of morphology models into a single one doesn't solve the entire problem.
But wouldn't the morphology model capture the similarity between those different mugs?
The graph does. I mean, I'm not sure. Maybe I understand what you mean by morphology model in this case, but that's essentially what we're trying to encode here.
Yeah, I mean, the morphology is basically just the information that sends up that the object exists at this location in this orientation. And I mean, we also talked about like that usually the sensor module would send a skip connection also to the higher level module, so we would get some point normal information there, which would be similar between the two cups, but not to the not to the.
I guess I've been thinking about this differently than you guys have been thinking about it. So maybe I'll let you go through this exercise here in the quiet room.
Okay.
Yeah, there has to be multiple types of information sent up, I
Right,
think.
it seems to be that's the case, and we don't understand all that, but it seems like we've in my mind, we sort of framed some of the constraints on this problem, and I think so far the presentation doesn't adhere to those constraints, but it's okay. I'll let you keep going, and I'll stop interrupting for a while.
Yeah. Okay. So some clarifications. We do not assume. So when we encode similarity in the SDR,
So now we switch to SDRs for sort of.
we are going to. Yeah.
Okay.
So what we're sending up is going to be an SDR that combines morphology, and depending on how we accumulate evidence, it can also combine features as well.
You're going to send up one SDR, and you're going to talk about how to encode things in that one SDR.
Right.
So if we change the way evidences are sent up, could we change, would that automatically
Yeah. So
fit in?
if
If we did what Jeff's saying and had different types of evidence or information, could you apply this technique to something like that?
Yeah, so there is a version, I think, I don't know if there's a version of that, but I think in Evidence LM, sometimes we can ignore features, or we can say that we don't want to use the features like colors or anything like that to add evidence. And if we don't do that, then the similarities that we encode are not going to consider features. It's only going to be a morphology.
And it would be pretty easy to accumulate those separately and have two different. And then you could easily have okay, this is the morphology evidence. This is how confident I am on this object given morphology only. This is how confident I am given things like color and lighting only.
Yeah. So this is the point. Whatever we accumulate as evidence, this is what gets translated into similarity in the encoded SDRs.
But yeah, I guess for what it's worth, or like a bit of context, I guess we didn't really maybe worry about changing that in the current setup because Monty does tend to predominantly rely on morphology already. Like if we just look at how it weighs different objects, it already does assign a lot of importance to the morphology. So we just kind of figured, okay, let's take those evidence kind of similarity scores and see how we can turn it into an SDR.
Yeah, and I think this is by design. I think that Evidence LM only uses adds evidence when there's good features, but it does not subtract evidence.
Yeah, morphology is treated differently than features, and it can recognize an object just based on morphology without the features matching.
Right. So in an SDR that we send up, we do not assume that there's a specific bit that has a meaning. So we don't say that bit 5 does represent some cylinder-like feature in the object, but we still are saying that similarity is represented as a distributed code of multiple bits. So the similarity itself is distributed on the feature on the bits, but there's not a specific feature for every bit, and hopefully that's somewhat addresses the capacity issues of encoding similarity. And also in what follows, it might seem like I'm doing some sort of deep learning, but I'm only using some optimization algorithms like gradient descent. I'm not really doing any kind of deep learning to encode those into SDRs, encode the similarities into SDRs. I'm not even using a single perceptron in this moment. So there's really no learning, and it's very quick because there's no weights to be learned. So the goals of this is to extract similarity scores from evidence scores. So we want to look at the evidences as we are looking at a cup or doing some sensory motor experiment, and we want to extract the similarity scores from there. And then we want to create.
Can you precisely define evidence scores?
So that's coming in the next slide.
Well, you're using it already, so I'm not sure I know what it means.
So when we are looking at an object and we have some other graphs in memory, when we're looking at that object, we can see we can accumulate evidence on the objects that we have in memory and this object as we are going through it. So
Just basically your confidence of what objects, a set of objects that you might be looking at and the confidence for them.
yes,
Is that right?
yes. So
Okay, so evidence scores is scores for the different objects that might be.
yes,
might
scores for the hypotheses. So
Okay, got it.
And then we're creating SDR representations from those scores that we accumulated from that similarity that we found. So these are two parts, and I'll go through them in details. Continuously adapt the SDRs to the new similarity targets. So in Monty, when we're learning from scratch, we keep adding more and more objects to the graphs. So we want those SDRs to continuously adapt to that similarity matrix can grow larger and larger. So we want to the object SDRs should continuously adapt. And we also want to maintain some sort of stability between the old objects that we have saved in the old SDRs that we have saved in memory and the new objects that we received in, so that the higher level it's expecting some object representations, and these representations shouldn't change too much, so that it can still represent hierarchy. And then maintain some useful SDR properties. We did some testing on that, but we still want to do some more. The limitations, as I talked before, I mentioned those, that if evidence LM is, for example, sensitive to some scale variations, then like, for example, two objects, they're exactly the same morphology, but one small cup and one large cup. These are going to, and we don't accumulate evidence on the large cup because the small cup is a different scale, then that's going to carry over to the to SDRs. So the similarity between them is going to be small as well in the SDRs. And so yeah, and also, as I mentioned this before, morphological features, if they're not, if only morphological features are considered, then the color will not be represented in the SDRs, or non-morphological features will not be represented in the SDRs. One thing that also I need to mention here, that we still need to store these graphs in memory. We will still, this is not a way to get rid of storing graphs in memory. We will still have those stored in memory. What we're changing is that what are we passing on to the next level?
That seems like an obvious thing, so I'm surprised you mentioned it. I mean, how could we not store the graphs in memory? That would be not knowing anything.
No, so
we're not using SDRs to store the graphs, I guess you're saying. You're just you're keeping whatever was there before.
So yeah, so after we convert those, after we create object SDRs for the graphs, we have to still keep the graphs, and we're only using those to send them to the higher level.
But isn't the graph the memory of the object?
Yeah.
So
we're not replacing the graph with the SDR.
I can't imagine how you could ever even consider replacing the graph. I mean, the graph is the definition of the object. So how could you not store it?
Well, yeah, I think you would always need to store it, but you're not storing the graphs as SDRs. Like in the brain, the graphs would be stored as SDRs.
Graphs are stored as pairings of multiple layers of cells associated with each other over time. And they would be SDRs, right? So.
But I think what I meant to say here is that one way of going towards neural representations is that if we can figure out how these graphs can be represented as SDRs, is that later on we can delete those graphs.
I think that's absolutely impossible. I mean, the graph is not a singular thing. A graph is a set of observations at locations, right? You can't get rid of that. That is I can't imagine it possibly getting rid of that. That's the whole.
Yeah, because I guess to clarify, like, yeah, because even if we went to grid cells, like, even though at any given time a grid cell activity could be viewed as an SDR, we would still need like multiple sets of active grid cells bound to multiple sets of active feature cells.
Right.
So yeah, like there's no way to like summarize an entire graph with
SDR. I think it's more accurate to say here that we're not changing the representation of graph. They're not SDRs. Yeah.
Okay, that's
fine.
underlying
in
graph
both cases, we
representations
would store
remain
it.
unchanged.
right, right.
And by the way, I don't know if it's clear, at least to me, and I think to Jeff also, like the synaptic, the dendritic synapses that are stored on active dendrites and things, those are also SDRs. Right, just to be this. So the permanent storage is also SDRs. It's not always just dynamic.
If Sumitai's suggesting, hey, we don't have to change the nature of our graphs, you're not doing that right now, you're just talking about creating.
Well, I'm not suggesting. I do think we need to change it. A
Well,
bit.
I'm just saying, but this statement on its own makes absolutely no sense to me. So
No, I agree.
it's like saying, well, we don't need to memorize anything. Of course we need to memorize stuff. I mean, it's like, so it just struck me as odd.
Maybe say explicit. No, not even explicit.
Yeah.
It's like it's a non-neural
not-
representation.
Maybe they say, yeah, this is not affecting how we store graphs in memory.
Okay,
You're only changing what we're transmitting
great.
from
Yeah.
learning mode.
This is changing essentially the common part of the common communication
Right,
protocol,
right.
in
We're not
particular
gonna
in the
change
case of hierarchy.
Right.
I'm not trying to change how we represent graphs, is what you're, maybe that's what you meant to say.
Exactly.
Yeah,
That's
this is not-
how I.
That's not what it says, but that's what, maybe what you meant.
Yeah, I'm still not quite sure I understand evidence LM, but maybe we can. I know.
Yeah, I have a slide.
I'm saying that doesn't.
Well, evidence LM is not the part that I worked on, but
No, I understand, but yeah.
okay. So how do we compute similarities from different objects? Let's say we have these three objects, and we're using evidence LM to do the matching. So we do this matching in a sensory motor experiment. So we're looking. So in every episode is going to look at a different object, and let's say that we have this sensor module looking at the fork right now. And before we start the episode, we have accumulated zero evidence on all of them. This is, by the way, a toy example. This is not a real experiment, of course. So after moving through after getting a sequence of observations with the action policy and all of that, we basically accumulate evidence on all of these objects. And we're just accumulating evidence on the similar objects. They will have a higher evidence score than the dissimilar objects. So we basically accumulated more evidence on the knife here than we would have accumulated on the cup, because there is not a sequence of observations that matches what we have seen on the fork for the cup.
Now, you're gonna do this, in theory, you're doing this for all the objects that this thing knows?
All of the objects all of the objects and all the hypotheses on all of the objects.
Right,
So
which is biologically impossible.
Right.
Just so we all understand that, this is the engineering way of doing it.
So is it a single number per object?
This is the maximum evidence. So every hypothesis is going to, accumulate some evidence.
For every pose and every.
For every pose and every location on the cup, and so these are all of the possible poses and locations, and basically this is what I'm showing here is the maximum. This is the best hypothesis from every object.
Okay, so at this point, it's a single number per object.
Yeah, the highest.
It's like 0 to 10, or it can keep going up?
It can. So we're going to normalize this, but it can keep going up.
Okay.
As we
Not normalizing it yet,
not yet.
okay?
Okay, so we're going to calculate the relative evidence with respect to the object that we're looking at, and so just relative to that object, and then we're going to linearly map it to the range of overlap bits that we want. So in this example, we're using SDRs of size 2048, so 2% sparsity of that will be 41. And so we basically linearly map it from the range -8 to 0, we linearly map it to 0 to
So
41.
these are the number of bits in the SDR that are active out of 2048.
This is the target. Yes.
This is the overlap.
This is what we're going to aim for, yeah.
Wait, not the total number of bits active, it's the overlap between
The overlap
these two.
between, yes. So this is what we're going to,
But isn't the maximum number 41?
Yeah,
so between itself, so this is basically between the fork and itself. So this will make it clear. If we put those in like a heat map kind of thing, this would be the row that we populate, right? Between the fork and itself, this is just going to be 41, and we don't really have to aim for that because the representation that we create is going to have to set.
so this is the desired overlap score.
Right, the target.
But yeah, like the knife would still have 41 bits in its SDR, but it's expected to have 36 overlap with the fork.
And that 36 comes from, how did you get the 36?
Just from the evidence score, so from the
Right, so
relative.
it's not a target, it's what it is, right? It's,
Because when we encoded it, we still haven't created SDRs yet. So
Oh.
that's going to be the target.
you're
for it.
saying this is, okay, so if I have infinite knowledge, I would know that the fork is supposed to have 36 bits
Right.
overlapping.
And then we're going to
Some
encode those.
pre-processing determined that or something.
Yeah.
Okay,
So that's what we're getting from the evidence scores. And then we can do the same thing for episode 2 for a different object, and then we get something like that. We just filled in the second row.
So could I think of this as, if you're just comparing those numbers, could we convert each number using our scalar encoder and then just do overlaps between them? Or
Convert which numbers?
the max evidence score?
So what we want to create is an object representation, not so these are only the similarities between them. The scalar encoder it's going to take a number and it's going to give you a similarity score. But we want
No, the scalar encoder would give you an SDR,
right.
given a number. And
But
then
it wouldn't be
numbers.
like there might be another object that would also have 10 evidence, but it has nothing to do with forks.
Okay.
Like the scalar value itself doesn't really tell us what we want.
Right.
It's the relative. Yeah.
Okay.
yeah, it's a
between
population.
particular object.
Okay. Yeah.
Yeah, well, we don't want to encode the similarities. We want to
Encode
create
the object
representation.
information. Yeah.
And the similarity is going to be calculated by the higher level LM. And same thing here for the last object. Now notice that these are not symmetric, and they're supposed to be symmetric, but because of the nature of how we're doing this, we just have to average those. So yeah, so basically we're creating symmetric matrices. So I'm just going to average these numbers. And
Why is it supposed to be symmetric? That's not obvious to me.
It's not supposed. So in a sensory experiment, it doesn't have to be symmetric because we can take different paths.
Right, it just doesn't, just inherently, I don't see why it should be symmetric at all.
It shouldn't be here, but when we encode the SDRs, it's a distance metric, and that basically a distance
So
from
if you're, the technique you're exploring, they need to be symmetric. Is that what you're saying?
when I'm exploring, they are asymmetric, and that makes sense.
No, you're putting it in a symmetric matrix, symmetric representation, because that's what you need to make this technique work?
Yeah.
Okay,
Because the similarity between A and B should be the same as B, and from B to A.
Yeah. Why do you think they should not be symmetric?
Or like the lack of symmetry is just kind of noise. Like we're essentially averaging over noise.
well,
Like if you visit the exact same points
well, if
and
you did,
and that's all points on the
right,
object,
right,
then
but you
yeah, you would
typically wouldn't, right?
assume that they're
Well, day to day, you wouldn't observe the same points. In fact, almost never would observe the same points. So,
Right.
So,
But just like
I
at a
think
logical
inherently
level,
the
you would
object
think, like-
similarity should be symmetric. It should,
well,
like if you're,
inherently, but not practically.
but isn't that what you want to convey roughly?
Well, I don't know, but it just wouldn't. I'm just saying, where does that come from? It doesn't come from observations, because observations wouldn't result in that. Observations would result in the thing on the left. So,
Yeah.
so,
Which is what we have, and I guess is the ideal.
oh, maybe it's the ideal, but if you're going to, but we wouldn't. A real system wouldn't know the ideal. Just wouldn't know it.
Yeah.
So, what neurons are going to look at this and say, oh yeah, these should be symmetric? It's like, no, I don't know. Okay, fine.
But,
I
I
got
mean,
it.
at a certain level, I feel like neurons could average over experience to kind of get something similar to, like, just basically to factor out the fact that, like, there's no importance in terms of the directionality of it. Like, if you observe the fork many times and you observe the knife many times, some cases you'll think of one more than the other, and yeah, you'll have this noise on both sides. But there shouldn't
Yeah, I
be
don't
any
think
like
it's noise.
one-directional bias.
Yeah, I don't think noise is the right word for it. It's just what you sensed so far. Like if you only sense the handle of the fork and you happen to think could also be a knife, that's not noise. It's just what you
Sure.
sensed. Yeah.
You're right.
I guess I just feel like any sense of a one-directional bias is kind of noise. But
Well,
Yeah,
like-
I don't know. I think in the real world this wouldn't be true, but I'm gonna let you go forward with it now.
I mean, in the real world, you would see many forks and many knives, and you could add up these scores over many times that you see these objects. So over time, it will become more and more symmetric without having to do this explicit
Well,
effort.
I think what actually happens is that you learn behavioral patterns that or seek out the answer, and you don't come up with these general overlap scores like this. I wouldn't, if I feel something like maybe the base of a fork, I would immediately jump to the top or if it just wouldn't be, it's not like we get all these points, we're gonna see them all over time. It's just not like that. The brain figures out action plans that are not symmetric. But I don't like it, so just keep going.
For what it's worth, we are using that policy when we're getting these observations.
Okay.
But yeah.
I also want to say that we don't really have to do this in a sensory motor experiment. We can actually do it on the graphs that are saved in memory if we want to. So like during sleep time, whatever, for the Monty system. And we can parallelize it as well. So if you just use these similarity scores, you can end up doing some sort of hierarchical clustering. And I don't know if this is. So you can see that cups are clustered together and Lego blocks and all, and I think Niels have showed something like this before. So.
Well, yeah, I think it was Vivian who first made this up. Yeah.
So.
No,
and this is based purely on morphology. Is that?
Depends on what you accumulate and the evidence. Okay. So. I think it has more weight on the morphology than it has on features because we don't subtract.
I'm guessing this is really gonna represent the similarity between objects. Often, small difference in two objects makes me perceive them as completely different. I know they're completely different objects because of that one small difference. And that's the problem I always have with this approach. It's like, I got this 1 bit difference here, there's 2 bits difference, but that's the difference that matters, and I don't glue up everything together. I sometimes completely separate them out. Like, this is the.
I feel like that's kind of an orthogonal problem that we could easily solve by basically outputting in the CCP 2 SDRs. You have like the general SDR, which is the one, this one, which is for generalization, and then you have the more kind of pattern separation SDR, which is going to be like completely random for every object. And that, so that would be like the Numenta logo or Numenta cup.
Okay, fine. That wasn't stated up front, so that was a possibility.
But I guess the problem that Ramy opened with the data sets, that's where we're really hoping that this will help. Like for example, we learn a dinner table set up with normal coloring, and now it's like medieval stuff. How do we generalize to that?
Okay.
But to your point, we would also have an SDR for like medieval cup.
All right.
And then that way we know we're on that scene.
It just, from a presentation point of view, it would be helpful to state that problem up front like that.
Right.
Like this is what we're assuming these things. Otherwise, I don't know that, and then I look and say it's not going to work.
Yeah, I think it's also hard just for Ramy to come in and have like 10 years worth of
historical.
I understand,
but it's also I don't want to sit here and just be silent and say I don't understand what you're talking about.
No, great.
So that wouldn't be useful for anybody.
I think the nature of his thing is to focus on very
I didn't understand that. If we talk about passing up one thing from one reason to another, that's not what we're talking about, because that's not going to work. You're saying, okay, this is an overlap similarity SDR, but it's not going to be sufficient. We'll have to have something else in addition. That helps me a great deal.
Yeah, I also have a slightly different view on the problem of that there might be one feature that gives you a completely entirely different similarity, and that is if you are moving. So I think it depends. It still depends on how you accumulate evidence, and that also depends on what motions that you took on the objects. So for example, if you're looking at an object and you know that it has a handle, and then your action policy basically tells you, I need to go check the handle, then you're not going to accumulate any evidence on the other objects, and that is going to be reflected in the similarity scores, right? So So basically, the action policy, knowing that this graph is different, is not going to, it's going to, during exploration, is going to go to the features that it knows is different or discriminative about this object. And if you're doing that in a sensory motor experiment, that you're not going to accumulate any evidence on the other objects. So, for example, here.
Follow that.
So are you trying to say that the objects will be more separated than?
Yeah,
Like
so basically you're going to go to the discriminative features because the action policy is telling you to go there because this is so for example here we're looking at a fork, then it's the action policy should be smart enough to say, oh, okay, so I think maybe that I'm on a fork, let me go to the tip of the fork and test what's there. And if we do that, we're not going to accumulate evidence on the knife because we have the difference in evidence is going to be large. So when we encode those into similarities, then it's going to inherit that they are different.
Yeah, or at least there's not as much evidence. But I think it like if we want it to be robust, that we say like this object is very different from this object. I think it is still useful to have that as a separate representation. Like that's just the way SDR bits or like SDR representations work. That it would be useful to have one that's like, okay, you can corrupt a lot of these bits, but I know that this is a unique object. Whereas like these two are going to have some overlap.
Yeah, I think you two are talking about two different things. I think if I, like a version of Jeff's would be like you have a fork where the right tip of the four little prongs, the right one is slightly dented, and that happens to be my personal fork
Right.
that I grew up with as a baby, so I really like it. And no amount of this is going to
Right. The example I have.
That's what he's talking about.
In my kitchen cabinet, we have a set of mugs that we got for my wife's birthday, and they're quite clever mugs. And they all look identical. They're like camp mugs. I like them. But one of them has a little chip in the corner, and it's just a discoloration. They all have the same mug. They all work the same. I use the same action policies on, but I do know that one unique. And so, oh, I picked that one today. And so I know that exists. I can look for it, but it's also identical in all other features. Right. So that's what I was thinking. It's just like what I said.
Yeah, I think it's relatively more identical, but you can still figure out that it's
yeah, but it has this, like in our case, we have like this metal thing that fell off during the '89 earthquake and dented itself. So we remember it. It's like a memory of our memory of the earthquake, you know.
In my body example, they're identical in every way except for a slight little chip discoloration in one part of the lip. Anyway, but it's like a separate object, but it's the same as all the others.
Right. So so we can have these hierarchical clustering figures. So now that we have this symmetric target overlap, now we can encode it into SDRs. So the target here would be, the goal here would be to generate 3 SDRs with these pairwise similar overlap bits between them. So if we start with the target overlaps, and I'm going to assume here that we have these target overlaps, we're going to create 2-way SDRs, basically SDRs with size of 10 bits and the overlaps between them. The number of active bits is 3, and this is just a 2-way example. So along the diagonal here we have 3 and then 0, 1, 2, just a 2-way example. What we're going to start with is a dense representation of 3 objects, and we're going to optimize these dense representations into giving us the SDRs that we want. So these dense representations are basically just float values, and the size of each dense representation is the size of the SDR that we want. Then
and they're randomly initialized.
Randomly initialized. We're going to use gradient descent to optimize them, and so we do the top K of them so that we can binarize into SDRs, and then we can calculate the current overlap between those SDRs. This is the pairwise overlap, so that we can calculate what the error is between the current overlap that we have from these randomly initialized dense representations and the target overlap. So that gives us an error. We cannot calculate the gradients. We cannot use this error to modify the SDR representations or the dense representations because this is it's not non-differentiable function, the top K. So what we do is that.
But again, I mean, as I mentioned to you the other day, we have done that.
Yeah,
We do have a way of doing that.
yeah. This is not what I what I ended up doing here. So what I ended up doing is I just moved the dense representations further away or closer, depending on the error that I have here. So basically, that error controls the pairwise distance. This distance is in Euclidean space, and basically what this is telling us is that if I have if I want the overlap to be higher, I'm just going to minimize the distance between the dense representations and so on, and vice versa. The gradient goes through this way here, and it does not go through the top K. Is this clear?
Is the loss just one number, or is it a loss for each of the cells and how they overlap?
So this is what it looks like. So the dense representations calculate the pairwise, and then the loss is going to be the. So for example, here basically I need to make them closer, minimize the distance because I want the overlap error is basically the target minus the current. So I multiply these values by the pairwise distance, and then I mean over them and then backpropagate. So it is, you have a matrix over all of the pairwise, and then you just mean because this is how we backpropagate.
Yeah, so it becomes a summary value at the end, but it's based on element-wise. Like in order to reduce the overall loss, we're gonna improve each element-wise value.
Yeah, and these are basically proportional to how much error that we have.
If you're older now.
I'm not.
Oh, okay.
Okay. So some results. We did some results on synthetic and some results in Monty. The synthetic are nice because we can do a lot of things that we can't do in Monty, testing the limits of the system. This is the baseline, kind of like we have 10 synthetic objects, and these are the target overlaps that we want, and this is a predicted. We start from here, and then basically we were able to match the target overlap that we want by just minimizing this loss. And it's very nice that we're able to minimize the dense representations, and that gives us the SDRs that we want with the features. We did some ablations on the SDR size, on the sparsity, and the number of objects that we can encode it with using this. And these are the results. So if I fix the sparsity at 2%, so basically the number of active bits in these representations are going to be different, and I fix this sparsity, and I change the SDR size, we can have, this is the overlap error, the average overlap error for all of these. So basically this lower triangle here, what is the average overlap error between this lower triangle and this lower triangle?
I'm just trying to see what error means in this case.
Error in matching the target overlap. So error in the pairwise.
Okay, so error is not error in any sort of recognition, it's just an error in the target overlap.
Yeah, and so this part of the presentation is basically just encoding that target overlap into the.
Yeah.
Could you go back to the previous slide? What's the input to this? No, the when you had the setup. What is the input to the system?
The target overlap. This is what we get from the similarities, of course, basically from here.
That's after it's been normalized kind of to the to be the SDR kind of bits that we want. So in the toy example it's 3, but here it's 41 out of 2048. And yeah, that's the only input.
It's just trying to find a representation which has these, but does it have to know what object it is? I'm a little confused. So
this is a very under-constrained optimization problem, right? We're telling it, find me 3 representations in this space that have these similarities between them. So it doesn't really have to know anything about the objects. We basically just want to encode the similarity in those SDRs. That's it. So it really doesn't really look at the actual objects. we only look at the objects when we're calculating how much similarity should be between them. That the representation is right.
Okay. And then when you're done, you will map the object ID to each of those representations.
Yeah, so basically we're saving, every graph now has a SDR representation, and we're just saving it, and we're always refining it with more evidence.
So that'll be an integer associated with each SDR.
A graph,
A unique ID
Yeah.
will be associated with each SDR.
Okay.
Or just the graph even, you don't even need to store the integer.
Itself.
It's just whatever the object, it's an object associated.
Yeah, it says object 23 will have this SDR, object 55 will have this SDR. And at the end of the day, you're gonna have these relative overlap scores.
yes, and then we're just gonna send them out.
You don't even need to say object 23 anymore. You just say, okay, this is the graph. When I recognize this, I will pass up this SDR that is basically the name of this object.
Yeah, but there's, what I meant is there's a discrete number of them.
Yeah, of
Yes.
SDRs.
Right, it doesn't know anything about the properties of the graph. It's not like two similar graphs will have similar representations. It's just if they happen to have similar overlaps, target overlaps, then they will have similar representations.
Yes, but it
Yeah,
happens to be
yes.
that the similar evidence scores correlates very
Yeah.
well with the similar graphs.
Yeah.
It's not actually looking at the graph, it's looking at the evidence
Right.
differences, so.
Yeah, so like I guess some totally different way of doing this might
Right.
be to like try and like put the graphs on top of each other, and like techniques Ben was exploring back at the start of Monty and stuff like that. But like, but this is really nice because like when we're recognizing objects, the learning module is naturally rotating objects kind of in its mind based on the most likely hypothesis and stuff like that. And so that's why we end up with these really nice alignments between like
Okay.
objects that are not just morphologically similar, but morphologically similar when they have like appropriate rotations to align with each other.
Right. But if you're learning a completely new object, which has its own graph, you have to do the comparisons with everything else.
Yeah, so this is an interesting thing, like a follow-up. Yeah, sorry,
Okay.
maybe Ramy, if you want to talk
Okay.
about it, but yeah.
Yeah,
Okay, so you're just, it's just finding 10 SDRs that have these target overlaps at the end of the day.
right, that's
Okay.
what we're encoding in the SDRs.
And you can't do that with some form of scalar? I guess not. It's there's a quadratic number of comparisons here.
Yeah.
Okay.
And in my mind, what evidence LM is doing is that it's basically aligning them, and then it's moving and testing all of these hypotheses, because the hypothesis space basically includes all of the rotations and poses and everything. So in my mind, this is really what it's doing. It's already been done for evidence matching, so why not just use those
Yeah.
scores instead of having to do it again?
So we talked a lot about the zeros last week. I don't know how that's handled here. And if you've
I have a couple of
the
ideas.
number of active bits.
We're gonna talk about the receiving end of these SDRs and how's that process?
I have not in this presentation, but I'm working on it.
That to me has always been the problem with overlapping SDRs like this. It's not that you can't come up with some way of coding it, but the way neurons work in recognizing patterns is problematic, right? And so you have to think about in real neurons, like, okay, now I have these overlapping scores. We're not going to try to recognize these things uniquely because it doesn't work for that, right? So what does it work for? I mean, it's sort of like you can't have your cake and eat it too. You can't say, oh, these are all similar, but I'm still able to tell them the difference, because if there's 80 bits or 100 bits on and only 2 bits are different, the receiving end really can't tease that apart. It's just might as
Well,
well
you
say,
can vary
well,
the threshold that you
yeah, but
match
it's
at,
two- it's
and then,
two
but then again,
dice.
if you have a separate SDR, like
You're right.
I think for generalization, like you would have some threshold that you could vary. You could say like, I don't really care what kind of
but-
dinner table I'm eating at.
Right, but the generalization part means I don't really want to tease these apart. I want to say these are all the same.
I mean, it's the same solution that we use for the features that come in from the sensor module. So basically, the receiving end does exactly the same mechanism that we're doing already for features like color or curvature, where we say, okay, these two shades of reds are very similar, so we're not gonna encode them uniquely. We just look at the similarity of these two shades of reds, and if they're similar enough, then both of them add evidence for that model. And we
Right,
will do the same thing with the object SDRs, or we could basically just calculate the union of those two SDRs, and that gives us a distance between the two. And if the distance is close enough, then we add evidence. If it's too far apart, we don't add evidence. That would be the straightforward approach.
yeah,
The
yeah.
implementation.
In the higher level, I don't think that we really need to distinguish these objects from each other, but that's only in the higher level. If we want to attend to that this cup is different from this cup, we need to go to the lower level, but the higher levels should only be dealing with recognizing scenes.
Well, I guess, you know, in the back of my mind, I'm thinking about how the neuroscience could possibly do these things. And in my model, which could be wrong, it's always been that there's sort of two representations that coming in. You have this mini column representation, which is not very sparse. And it's sort of like you're, it's not very large, it's not very sparse. And you're essentially, and that's what we call the, you know, the spatial pooler. It takes a whole bunch of patterns and maps them into a much smaller set of patterns. And therefore you've got the similarities there. You know, you don't really tease things apart. But then you have to run it through the sparsification process, which says, okay, under these different contexts, I really want something unique. So you have to have a unique and a non-unique representation.
Yeah,
and then here you're trying to do this is the non-unique representation, but you're trying to do it with more objects. Is that correct? So I'm trying to understand it.
But it's done in a way
we're
that
trying to be able to do it.
Encodes the morphological, the graph similarities as
Right.
as dictated by the evidence.
So I'm now trying to imagine, okay, I got region 1 and region 2, or column in region 1 and column region 2, and I'm passing this information up. Well, we've already said I have to have a unique
Yeah,
version.
which this is not.
And then a non-unique version. So I'm just trying to make it all work. I'm trying to
So
make
the problem with the spatial pooler representation is it encodes just the feature similarities. It doesn't have the graph similarities in it.
Right.
So this will have graph similarities as computed by the evidence algorithm. So it's got whatever the limitations of the evidence algorithm, which does have graph similarities, this will be able to encode that. So this is in that sense better than the spatial pooler representation.
Yeah.
maybe we can
And-
have
and
a
like-
meeting sometime where we talk in detail about where we want to encode similarities and where we want to encode things uniquely, and also how we best do that with SDRs, and let Ramy present his slides, because I feel like he came up with a really nice algorithm.
Okay. All right.
With a bit of a unrelated, like next.
Well, I'm trying to make it work, right? I'm trying to make it work in my head. Like, how am I going to get the whole system to work? And this is a piece of it. But I can just let it go and just say, okay, I don't know how the whole system is going to work yet.
Yeah, I think that the core of this, if I understand it, once you have a set of pairwise similarities that you want to, how do you create SDRs of them? Which is not an easy problem.
Right.
So that's what he solved.
Right.
And then we can use that where it's a technique we can use wherever we want.
Yeah, but I think as a technique, I have to be convinced it's usable. And I have to understand how neurons will take advantage of it, whether it's really practical or you know, I don't want to say just because you did it, it's we're done. It may not be right, you know. I mean, it's a good, interesting result. I'm not taking that away from it, but it's like, okay.
It's another way of creating similar. The spatial pooler is one way of creating it,
Right.
with purely based on static features, and here it's based on a graph of some sort.
Right.
So that's the
Yeah, and I'm just trying to lay it on the neuroscience thing. Where do these things exist, and how do you pass both these representations up, and how the neuron's going to tease them apart, and all that kind of stuff.
So it's not clear from the slide, but the algorithm you implement is extremely neurally plausible.
I'm not objecting to that.
Yeah, and
Yeah, I
I
mean,
think
we-
we could keep talking more about this, but I feel like that's a whole discussion that's maybe not so related to Ramy's project.
Okay. I'm trying to understand the whole thing.
So these are just different ablations. I just wanted to make sure that it works for different ranges of SDRs at different sparsities. So a 2% here, will be like 21 bits and so on. That's the overlap error in matching the target overlaps. So this is, if we create these representations and then we try to compute their pairwise overlaps, this is the kind of error that we're looking at, maybe like on average 1 bit if we're looking at this number of, this size of estimate. Now, of course, because I try to normalize this overlap error by the number of active bits because I feel it's not fair. It needs to be normalized by, let's say, this representation of 1496, it has 81 active bits. So, you know, one overlap error is, you know, very little compared to the others. So when you normalize it, this is kind of what you get. So the 1024 is a bit of a high normalized error, and as you go up, it seems to be kind of the same in normalized.
I mean, no matter what, these are tiny numbers.
Right.
Because this is out of 41.
Yeah, this is like half a bit in error.
41 to 81.
It's pretty small.
Yeah, I mean, even at the max, it's,
Right.
it doesn't matter.
Yeah, I was just hoping for this, like basically those two here.
Yeah, but at
kind
this
of like
scale,
the
I'm
same.
not sure it matters.
Yeah.
Yeah, just half to 1 bit.
And then I fixed the SDRs at 2048, and I changed the sparsity, and this is what it looks like with changing number of bits.
Yeah, I mean, that number could be 5, it would be, or 10, it would be still fine.
Right. Varying number of objects, this is kind of the trend that we're seeing with more objects, so 10, 50, and 100. Also, again, this overlap error on the side here, and then.
But yeah, just on your point, Subutay, if we make it too sparse, like if it's 5, then we have less chance of encoding a lot of different objects.
No, not at all.
Perhaps.
I mean,
Like
in
I think
2048,
Subutay, you were saying we could have 5 bits of error and it wouldn't matter,
Yeah.
right?
5
Not that
bits
you were
of
saying
error.
we would encode it with
Oh,
5 bits.
you mean the bits of error?
I'm just talking about error. He's talking about overlap error here, right?
Yeah.
And so an error of a few bits is nothing in out of 41 bits on, or 81 bits on.
Yeah.
That's what I'm saying.
Okay, yeah.
This is what it looks like in Monty. This is it's different from this because this here we have for synthetic we have the full target overlap. In Monty we have we're basically filling those rows one by one. So these are the kind of results that I got.
Yeah, I'm not sure. I think you'll have to explain what's going on here.
Yeah.
I don't
So basically, it's the same. It's a target overlap scores for 77 episodes. Basically, we're looking at these objects in the YCB dataset, and we're going through them one by one. And every time we finish one object, we basically add that row to the target overlap. The challenge here is that it needs to adapt to adding more and more objects every time we finish an episode, right? Because we don't see all of them at the same time.
I still don't know what's going on here, but maybe if it's obvious to everyone else, I don't know what prediction.
So I think he's learning. You're learning objects in an incremental fashion here.
Yeah.
So
So
one at a time. So that if you've only learned 3 objects, you can only have a 3x3 matrix of similarities. The rest of them are random.
What is prediction and target though?
So predictions is a wrong word, but this is the current overlap. This is the current overlap. So this is similar to that, basically.
Just go back to just
This
use
is
words.
the
Just use
predicted
words.
overlaps.
I'm sorry,
from-
so,
The one on the left is basically showing the SDRs that the algorithm has made and how good they are at clustering. The one on the right is what we want them to look like. And so the good thing about this graph is they look very similar.
okay.
But you can only do it up to this.
Yeah,
point,
prediction
right?
isn't the right word then, right?
Yeah.
Predicted.
There's only a square in here. I don't know if you can see my mouse, but
Yeah, I understand that.
yeah, there's only a square in here that matters. The stuff to the right
Right,
and the bottom
right,
don't
right,
matter.
right.
Is that right?
Right. As we see more, like I showed in the previous evidence.
Yeah, if you can.
scores.
Yeah, I don't know if you can.
What is
pause
the
it.
correct word for the left, not prediction, is actual?
Yeah, current overlaps maybe. Current, and this is the target, or
Calculated? I
yeah,
don't know.
calculated overlaps maybe, or trained overlaps,
Okay.
or object SDR overlaps.
Like algorithm result
Okay. So why'd you call it prediction? I don't get
And yeah, deep learning terminology we use really.
Oh, is that right? Is that the, you know, the
Yeah,
word?
whatever the network outputs is usually prediction, so it's stuck with me. But
Yeah, but I think in our context, prediction is
Yeah.
something completely different.
Right.
the model's prediction.
Yeah.
Yeah, right. Yeah. So
Okay, I got it.
Okay.
No problem. I
and
got it.
it's increasing because we keep adding to it because every episode.
Yeah, got it.
So when it goes from 22 to 23, it's gone through a bunch of iterations and settled, and now you're showing the
Yes.
actual. Okay.
Yes.
Okay.
This is the error after the bunch of iterations. So basically, it's supposed to stabilize like this after every episode. This is the error in there.
What's an episode?
Basically, looking. So after we add each row, that's an episode. So look, doing a sensory motor experiment on one object.
A new object. Episode's a new object.
Every episode's a new object. So this is the error after training the encoding algorithm to see that, to encode this.
Error after each new object. Or something like
Yeah.
that. We can call it that.
But okay. No, that's not right. Because the scales don't match between the left and the right. Because the scale is now at 260 to 70 objects, and then, oh no, what is the number on the right there? The 409, 425, 435.
This?
Yeah.
This is just so I have 77 objects, but I'm showing it like 10. 10
Okay, so
every-
divide by 10 is
Yeah.
the number of episodes.
I'm showing 10
Iterations.
iterations per.
Okay.
Yeah. I have more detailed slides when I presented them to the team, so I just copied those visualizations. This is what it looks like on a TSNE. So basically, I took the trained object SDRs, and then I plotted the TSNE is basically a dimensionality reduction algorithm. It tries to map the representations into a lower dimension while
What does
maintaining.
TC stand for? I'm not going with that term.
Uh,
Is that a standard term?
it's I
It's
think
a standard. It's just doing similarities, trying to project high dimensional similarities to two dimensional.
Yeah, while
Okay.
maintaining
Similarities.
the similarities,
It's
yes.
related stochastic neighbor embedding.
Yeah, the
Okay.
T I think is for the T schedule.
It doesn't matter. It's basically dimensionality reduction
Right.
in a way that you want to keep similarity.
Yeah, so it's not linear as opposed to BCA. Yeah, so basically what it's doing is that we're seeing that similar object cluster kind of clustered together.
And to your earlier
Well-
point, like things like scale and the use of color and the evidence accumulation and stuff like that could explain why the clustering isn't perfect. And then I guess, yeah, also like trying to cluster quite a abstract space into just 2 dimensions is also challenging. So
Well,
overall, this looks pretty positive.
I see a lot of cylinder things that are not all in the upper right there, so I'm just wondering.
Yeah.
Yeah, like on the
Yeah,
left.
it could be
there's a
scale.
chef
Right.
And chef can, and on the right there's a tomato soup can.
Right.
They're
and there's
basically
there's
cans.
Another
I
thing.
mean,
that's
if you
rounded.
if you would add a 3rd or 4th dimension, it might look totally different again, and they might be similar on one dimension, but then different on another dimension, like color.
Right, so this is done just for visualization for us.
Yeah, yeah.
Okay, so this is
It-
not an actual result, this is just visualizing something that may be perfectly correct, but the visualization still
Yeah.
struggles.
Yeah, because of 2D.
Got it, okay, so you can't collapse.
Yeah, it's kind of like a nice sanity check that it's working well. Like
Well,
if this was if it looked random, then. But
Right,
yeah,
it's
I think ultimately, as Ramy was pointing out, like, well, we need to, like, it doesn't seem like there's the limitations with the algorithm. It's more about like just getting Monty to represent things that are similar better, like being able to address scale.
When you do the projection, is there some kind of significance where you try to orthogonalize it or try to find the most significant dimensions when you're doing it, or do you just map it to, the random lower 3 dimensions or whatever?
No, I just map it to a 2D dimension, and I define the distance function as the overlaps between the SDRs.
But am I correct in saying that this is irrelevant? This is just like, you know, it's nice to see that it looks maybe like it's doing the right job, but the actual overlap is what matters.
Right. Well, yeah.
Right.
But we don't know if we're extracting.
Well, I could just take the chef can on the left there, and I could actually look at the bits in that, and it might overlap with those other ones up there, just in some sense, right?
Yeah.
It should.
Yeah. So, and this is also an iterative procedure. Sometimes I've seen these t-SNEs. Sometimes some clusters basically just move, snap together. Like, for example, this part over here with these balls, tennis balls, and all that. Sometimes basically it will just snap to the lemon and all of that, and sometimes it separates. It uses gradient descent, and sometimes it struggles to also map them together.
But you're not changing the SDRs underlying when you're doing this, right? It's just a visualization technique that's flawed.
It's just visualizing it. I mean, the ultimate measure of the SDR encoding is the loss between those two matrices that Ramy showed earlier. But that's a bit hard to see, and this is just nice to look at.
Okay. All right. Well, actually, it distracted me because the other stuff is a real McCoy. This is just.
Well, yeah. So we don't really know if we extracted the right evidences. We can look at a heat map and we can see, okay, so this object is similar to this object based on the heat map, but we don't really know if we. So this will tell us that the encoding algorithm works, and also that the evidences that we extracted work, because it means that they would be closer together than random representations. So similarity is kind of extracted.
And I think the first time you made this, actually, it didn't look like this, and it helped.
Yeah, it was random. Yeah, I should have.
And was that because it wasn't encoding it correctly, or because we weren't using the TSNR thing correctly?
Yeah, I had a bug in the code, but that showed basically how if it's random, it looks completely different. Everything is all over the place.
Right. Well, I was wondering about these outliers. If that, some of these outliers look like they're mistakes, but they may not be mistakes, right?
One thing we could do to check is to actually look at the tennis ball object SDR and the lemon, for example, and
That's
see.
what I just said. I said that you look at the SDR for the chef can and the other cylinders, and you could just literally look at them and see if are they overlapping properly.
Right. Yeah.
And another thing that might be helpful is give a reference frame. So generate a completely random one and show it to us and be like, this is what the random would look like. Here's what it looks like. So we can at least have a reference frame to something, because I have nothing to compare this to.
Yeah. I have a figure later on Slack channel. Maybe I could bring it up.
Yeah, I mean, that's it. I mean, you could show this before the learning happened.
Yeah, before that.
And before and after, yeah.
Mm-hmm.
But there are some obvious examples, like, for example, the Phillips screwdriver and
Obvious examples of what?
of objects that look similar or are kind of clustered together. Like, for example, these two objects, the knife and these utensils, they kind of look similar. Toy airplanes, I don't know. These are not toy airplanes.
They're parts of a toy airplane that I guess someone in the YCB world would build.
Yeah.
But here you have a medium clamp and a large clamp. They're not near each other, so.
So
I think we can spend too much time looking at this. I don't think
it's not that useful.
It's just like a quick visualization.
Yeah.
Yeah, but also to Neil's point, it doesn't really capture the scale. So this is a medium clamp and a large clamp, and the scale is not captured because of the evidence way for what we're doing. If they were the same size, then they'd probably be closer together. I don't know how much more time we have.
I don't know, 10 more minutes?
I guess 15 minutes. Yeah.
I think it'd be good to have a 5-minute break in between.
What's next?
We have our models training meeting.
I see.
I did some experiments on streaming objects, just basically streaming also is not very, I was just basically adding more objects. So I start with 10 objects and I keep adding 10 and 10 and 10 and so on. And then I look at what happens to the error as I train more. This is an experiment to test for that the SDRs are adapting to more and more objects as well. And this is kind of like what the error looks like. I'm hoping to see this as we add more objects to the target similarity. It goes up, and then the optimization brings it back down. So yeah, as expected, I guess.
Is this with having the first 10 SDRs then frozen, or do they keep changing as well?
No, in this example, they keep changing. These are the results I showed before. I haven't done. I should do these experiments with also stability to see how the error would change. But
Yeah, did you see how much these original SDRs changed after you added more objects?
no, not really. I know that they change a lot, but the stability PR should help fix that. But the thing is, so I know that the stability PR fixes that, but the thing is would be to look at the error and see if the error is still manageable. Because some of these changes, they need to happen. Some of these SDRs, they need to move because we're adding evidence to either bring them together or, so there's some distribution shift there. Yeah, some extra experiments. I don't know if we should go through these, but basically not giving them enough time to train, and this is what it looks like over time.
What if you, I mean, you picked like a, was it 2% sparsity here?
Yeah.
What if you picked a much higher number, 10%? What would it do?
For the streaming?
Just the whole thing. You take the entire algorithm you just did here, and you didn't make it that sparse. You made it less sparse.
I used 5% here, but
what about 10%? What I mean, I'm jumping ahead to the problem of forming unique representations. The reason I always thought that these overlaps would not work is because they do not allow you to determine unique representations. The neurons don't, you know, they won't be able to tease apart these different objects, group them all together, and you can't get around that. And you need to be able to form a unique representation. So it's, if I understood from the beginning, the exercise here was to form two types of representations, one that's unique and one that's non-unique. And then I would have been much more amenable to this whole approach. You know, I feel bad because I've been arguing with Niels about this. This isn't going to work. And the reason I think it's not going to work is you can't tease apart these overlap representations. But now we're saying, no, we're not going to try to tease them apart. We're going to have separate representations that are unique. So one way to get between the overlapping SDRs and unique ones is to go sparser. You can start with these, you know, and that's what I'm asking. Like, what if I had a 10%, 10% sparsity for these overlapping SDRs you've been describing here, but I want to form unique ones by subsampling from those randomly.
Then, yeah, so you can do that to a degree, but I still think you would want to do that alongside having completely random unique SDRs, because like that won't be as robust. So like, yeah, I think the way it was in my head is like if you had like a higher level learning module, it would basically have two matching filters for each point. Like you move to a point, what has it learned there? It's learned a unique SDR from the lower layer. And that's what the very specific object was. That's only for that thing like Numentamug. And then it's learned like the more generic SDR. Let's say that's from a different layer. I don't know if that's layer 2 versus 3 or whatever that it's receiving the input from. And then, but that one, I think it's important that you can vary that threshold. So depending on the context. So if you say, oh, I don't really care what dinner table I'm sat at, I just want to be sat at a dinner table, you're going to lower that threshold. And as long as you see, you know, okay, this is a cup.
So
but then, yeah.
The reason I didn't want to go that way is because I don't really have any evidence that there are two sets of neurons projecting up the hierarchy. And you really only have, you know, evidence of one. And at least from layer 3, for example, the paper I just reviewed the other day said they said layer 2 didn't project much, although I believe them. But so one possibility is you could have the same population representing both the sparse, the highly sparse, and the less sparse one. And that's easier to do. That's kind of easier to do in a sort of time sequence type of thing. Maybe like in one part of a phase you get the denser one, next part of the phase you have the less dense one. But I think your point was, Niels, as you said, if you did it that way, you just, you know, you're subsampling these denser representations, you'd have more errors, is what you're saying, I think.
Yeah, it's a trade-off.
Well, imagine I had 4,000 neurons and I had 10% active, then I have 400 cells that are active at one point in time, and then I go to a moment later, I have 2% because I have 80 cells active. There's a lot of ways you could pick that 80 out of 400 and still uniquely capture it. I think there would be. I'd have to work on the numbers. So it's not clear to me it wouldn't work. But we have that sort of dichotomy, that basic decisions, like, is there one set of cells that are doing all this, or there are two populations of cells? And at the moment, I don't have much evidence for two populations. So I'm trying to think of some way to make it work with one population. But, maybe layer 2 does project up, and people just didn't see that. I don't know. That's why I was asking, would you get the same results, similar results, if you had a less sparse?
Yeah.
Well, it's not clear how sparse this is. I don't know if you did the active, how often each bit is active.
Yeah, towards the end.
Well,
Okay, yeah, maybe we should try to wrap up
Okay.
because it's,
But in general, I think the higher dimensional you make it, and it's still sparse, it's just going to get easier. Like, I don't think that's going to create a challenge for this approach. Is my intuition, at least.
well, it wasn't.
And I think that's consistent with your results with the overlap error and stuff like that.
I'm not sure yet. I had a question when I talked to him last time. How many bits are actually on during the entire cycle? What is the duty cycle of each?
Yeah, I think that is
suspicion-
a good point. But we could add some regularization to get that to be better.
Yeah, so
We had to do that with the spatial pooler, by the way. We had to add a regularization factor to make sure all the bits were used.
Yeah.
Yeah, so because we are forcing some like specific overlaps, these overlaps are
Yeah.
high, then there is going to be large populations of dead neurons, and
Exactly. Yeah.
and that's just a matter of this is by design.
Well, you don't want that.
Yeah, you don't want that.
That
Then it's
is-
not a useful. Then it's not really an SDR.
So, right, spatial pool had the same problem. We had dead bits and we didn't like it. So we put in a factor that basically boosts the activity of dead bits. They don't like
Well, I
the
mean, this is just a function of how many objects you have. If you only have 10 objects, but you have 2,000 bits and you want the 10 objects to have some overlaps, you need to have that numbers.
Right.
But once you have
It
1,000,
is a problem. If you have a lot of objects, then you have better utilization, right? We saw the same thing.
that's what Ramy's
Yeah.
plot shows here, I think.
I think that's part of it, but also the other part is, do we want to do unions or not? And if we want to do unions, then you need.
I don't think you'd want to do, I don't think you could do unions on this type of thing. Or I wouldn't assume you wouldn't.
I think you could, because you could have like, well, yeah.
You
I
could
don't
do
know.
maybe a little bit.
Well,
Yeah.
you can't do unions when you get less dense, right? I mean, less sparse. To make the density make it, the unions don't work.
Exactly. Yeah.
So I guess I'm sitting here going, hey, could I do this as a single population of cells? These representations would be less dense. Therefore you wouldn't form unions. But the sparser ones, in some sense, if you were subsampling from this overlapping population, in some sense, the overlapping population is a union of all the unique ones. Right, that's the way to look at it. It's a it's a union of all the unique objects. So all the unique cups, I take them and I form a union of them. I get this representation.
Unique is the opposite of encoding more overlaps.
Right. This is the problem. You need to both. How do you do both in one population? Where do you have two populations?
Yeah, but for now it's one population, but I still think you could do unions in the sense that, like, let's say you're just very early in inference and you don't know if it's a cup or if it's like I don't know, something very different, like a ball. Like, there's nothing stopping this from representing the union of those two SDRs in one SDR and passing that up. But of course, like the more similarity, the more similar like the representations, you're basically going to converge to the sparse like what is just like the most likely hypothesis.
Yeah. And this has to be counteracted with what Vivian's saying, is if you have objects with similarities between all of them, then that's forcing you into a denser representation.
Right. One of the ways that this, I don't want to get too far, but one of the ways this probably works in the brain is that you have this very fast inhibition, which is enforcing sparsity. But that is fast, but it still follows on the initial activation. So you could activate a whole bunch of stuff really quickly, and you have this very dense representation, but very quickly it's going to get sparse. You know, it's a time-based thing, right? So you can say, oh yeah, a union real quick, but then quickly you go to, I mean, that's how we did the temporal memory work like that, and that's what would happen in neurons, right? They could become active. They all came active at the same time, but then the inhibition would quickly shut down most of them. Okay.
Okay.
All right.
Anything else?
Just a comparison between synthetic and Monty. So this was in synthetic, and I had a hunch that in Monty it would be slightly better, less dead neurons.
What is? I'm not sure I understand these two charts.
Yeah.
In the left, the previous one, what is the x-axis?
Sorry, I forgot. This is number of objects, basically 10 objects, 100 objects.
And before your learning algorithm.
Yes.
And
So
after
the-
your learning algorithm.
So
Okay.
the blue one is random.
Yeah.
And this is basically after learning. Here is the same thing, but these are synthetic experiments, basically synthetic, so some random target similarity. And this is the actual target similarity in Monty, because when we discussed this, we showed that there's a lot of low target overlap, and there's just only a few bits of high overlaps, target overlaps. So in Monty, it will do this thing where, you know, there's only a few ones that are very highly similar objects, and there's a lot of low similar objects. So that
And this
contributes.
has to be with zeros in the matrix.
It's not zeros, but it's lower
Some low
version. Yeah.
overlap.
So low overlap will contribute to less dead neurons, basically, because it's not forcing that high overlap anymore between too many objects.
But if every object has to have at least some overlap with any other object.
Yeah,
then
I think it's easy to
you can't
address
have,
this
they
like,
can't be more than 80 bits apart, right?
but like, yeah, if I think you mentioned maybe to Ramy, like, yeah, we could have a threshold where it's like, okay, if there's
Yeah,
if
yeah.
they're below a certain amount of overlap, then we just enforce that they have no overlap.
That's what I'm
That
talking
would-
about, the
that-
zeros.
That would significantly reduce this, but it's just something we haven't done yet.
Yeah, but I'm
Yeah.
still confused about this, like even here, if every object has to have at least one bit of overlap with any other object, then the representations cannot be more than 80 bits.
Why would they have
Hard.
to have overlap?
Well, that's what he said. He said there's no zeros in the matrix.
It doesn't have to be. So what I'm saying is that if there's high overlap, that makes more dead neurons, and there's low overlap, that makes because they now have to go and take other neurons that were dead before, just to
But the
represent.
furthest two objects can still have to have some overlap. So you cannot use more than 80 of the bits. I don't think.
Why are there no zeros in the matrix? I mean, you can have negative evidence for a lot of the objects.
I'm just reacting to it. He said there's no zeros.
There
in
could
the
be
matrix.
zeros, but there's
The experiment
I
doesn't
think-
have zeros. So so I don't understand how you could have so many active neurons.
so.
You understand what I'm
so
saying? It's
many-
just
they're not-
if there are no zeros, and every representation has to have at least one bit of overlap with any other representation,
Yeah, so
the
77
entire
objects.
space of neurons that are used cannot be more than about 80. Am I wrong in my logic?
Why 80?
Because you're using 41 at a time, and so the furthest something could be,
Here it's
Yeah,
only two
another
objects
40.
only, right?
no, but
Yeah,
that
there's
means
100
all of them.
objects.
Yeah, 100 object, but every object has to have at least one bit of overlap with every other object.
Well,
so
yeah,
Okay,
I feel
maybe
like you
my
could just have,
logic
like-
may be wrong. Yeah, my logic may be wrong there. I need to think about that.
But Ramy, why are there no zeros in the matrix? Wouldn't we have zeros, especially after
Yeah,
normalizing? If they're-
Yeah, there could be zeros, but the point what I was trying to say is that because we have a lot of low values in the overlaps, then this will spread to occupy more of the dead neurons. This is what I'm trying to say. But there could be zeros. When we normalize, there will be at least one zero in a row. Yeah, so we can wrap up here, but
Okay.
All right, that's good.